Okay, so in this particular video, we're gonna visualize the solution that we had obtained in the last video. So essentially, we want to plot the stream functions of the Moffatt solution. So I clear all the variables and clear the screen. Let us first define the Cartesian first quadrant. So essentially what I have defined over here, they are the x and y axis spanning from 0 to 1 and 0 to 1. Now we want the matrix product of these two arrays. Essentially this array and this array should be able to give me the entire grid points corresponding to the pair of those values. And the function in MATLAB that helps me do that is ND-grid. So I assign the pairs of values capital X and capital Y, and it is defined as ND-grid x comma y. So if I run the program, I can see that capital X is 100 cross 100 and capital Y is 100 cross 100. Now, because the solution that we had obtained was in the r theta coordinate system, we must first define what r and theta are. Let us quickly see what the solution was. The solution looked something like psi equal to minus u r by sine square alpha minus alpha square times alpha square sine theta plus sine alpha cos alpha minus alpha times theta sine theta minus sine square alpha theta cos theta. So this was the solution, and this is sort of the solution which is valid. So let us draw the schematic of the problem. So this was one plate and this was the other plate. So this plate was moving at a velocity capital U while this plate was stationary and this angle was alpha. So clearly this solution is valid over the range of thetas 0 to alpha. So what we have done so far is defined the Cartesian space in which this will lie. So this is sort of the origin. And in this particular space, in this particular region, this particular solution is sort of valid. So we must first define what the r theta is. Essentially, the r theta coordinate system r and theta. So this is y and this is x. So r is square root of x plus y square and theta is tan inverse y by x. So this sort of defines what the coordinate system is. So let us go back to MATLAB. We have r equal to square root of x square plus y square, and similarly theta is equal to a tan 2, which is tan inverse y comma x. A tan 2 appropriately assigns the sign of the tan inverse because tan inverse can have a non-unique solution. So first and third quadrants are the same, for example. Second and fourth quadrants are the same, for example. But A tan 2 looks at the appropriate sign of x and y and decides which quadrant actually the angle should lie on. And clearly, because x and y in this case are positive, all the thetas will lie in the first quadrant. Let us define the solution. So psi is minus, so let's assume that u is 1, so it will be minus r divided by sine alpha square minus alpha dot star, because we have element wise multiplication, alpha square times sine theta plus sine alpha times cos alpha minus alpha times theta dot star sine theta minus sine alpha square times theta dot star cos of theta. And once you start encoding this, you should be very careful with the brackets, because it is very easy to mess up the brackets. But anyway, so now we have defined the solution for psi. Let us have a quick plot. Figure 1, contour. So but we must remember that despite the solution for psi existing in terms of r and theta, but we actually have to plot it in a Cartesian space. So the contour will exist only in x and y, not in r and theta, but the plot will be that of psi. This is how it will look. Okay, there appears to be an error. Let us see what the error is. Error using alpha, too many output. Okay, so we have not defined alpha, and that is why MATLAB has interpreted alpha as one of the sort of base functions that it has inbuilt in its library. So we must define alpha. So alpha, let us call it as pi by 3. Okay. Okay, so let's see what the solution looks like. Okay, solution looks something like this. Let us fix the aspect ratio of the plot. Because the plot is that of a physical condition, I mean it cannot have a weird aspect ratio, it will look odd. Okay, so the x and y axis are now equal, looks more or less okay. But we must not have a solution beyond alpha equal to pi by 3, because there is no fluid beyond alpha equal to pi by 3. What I am trying to say is, beyond alpha equal to pi by 3 there is no solution. The solution is bounded in this particular region. So what should we do? So we do a small trick. So psi of all values such that theta is greater than alpha should be set as nan, because once you set something as nan, it does not come up on the plot. So the meaning of this is, find all those thetas which are greater than alphas, all those indices which correspond to theta greater than alpha, the psi of all those indices which correspond to theta greater than alpha should be set as nan. Okay. This is essentially what this particular line means. Let us again plot it and see whether we have some progress. Okay, excellent. We only have the streamlines which are corresponding to the domain that we have, but we should ideally want to plot the plates as well. It's good to show the plates as well. So let us do that. What are the coordinates of the plate? So look, if this is the coordinate system, this is the origin, this is 1 comma 0, and this is the other plate. So let us say the plate extends till 1. I mean it extends to infinity, but we want to plot it till 1. So this will be 1, and the y coordinate of this, because this angle is alpha and this distance is 1, so this y coordinate will be tan of alpha, because tan alpha will be equal to y by 1. So essentially y becomes equal to 1 times tan alpha. So this coordinate is equal to tan alpha. Okay, so in order to make the x-axis, we have the points as shown. So the x coordinates are 0 and 1, and the y coordinates are 0 and 0. So the plot function plots all the pairs of x's and y's. So x's pair will be 0 and y pairs will be 0 and 0. So the x coordinate pairs are 0 and 1, and the y coordinate pairs are 0 and 0. Let us draw it as a red line with a good line thickness. So this is the x-axis. Similarly, let us plot the y-axis. So the same logic holds true. So for the y-axis, the x here will be 1 and the y is tan alpha. So the x pairs are 0 and 1, and the y coordinate pairs are 0 and tan alpha. So let's do that. Let's plot it with a blue line. This is the y-axis. Okay, excellent. Okay, I think we have plotted much more than we want, but we can fix that. We can set the y limit till only 1. I mean, we don't need this remaining plot. So let's do that. Let's set y lim as minus 0.121. We shift it slightly to the negative side so as to clearly see the plates. Okay, so excellent. And in a nutshell, this is how you visualize the stream functions. And I think for the assignment problems also, you will take your time and make the plots, because this helps you visualize how the structure of the flow looks like in a much better manner. The red plate is dragged from left to right, and so the flow is sort of induced from the top to the bottom. How do I know whether the flow is induced from top to the bottom? Well, the answer is really simple. With the help of the stream function, you are in a position to now evaluate what the velocity field will be. With the help of the velocity field, you can make use of the quiver plot. I have shown how to make use of the quiver plot in an earlier video, and I will not repeat it in this video for sake of time. But you should do it. You should try to obtain the velocity field analytically, and it is very easy because you have the expression for psi. Once you have the u fields, set the u fields for theta greater than alpha to be nan, and then just do a quiver plot of the velocity field. So with this, we end this small yet instructive MATLAB video, and I will see you next time. Bye.